Today, I'd like to talk about several peroxide species formed on calcium oxide by the decomposition of nitrous oxide. A variety of absorbed oxygen species formed on metal oxide by the molecular oxygen, by the absorption of molecular oxygen. For reactions involving nitrous oxide, the formation of O- species are frequently discussed. However, unidentified absorbed oxygen species are recently reported to exist on the alkaline metal oxide. In the present talk, I'd like to show you that the surface peroxide species were formed on calcium oxide by the decomposition of nitrous oxide. I will also talk about the surface sites and reactivity of surface peroxide species. Catalyst is prepared by the decomposition of calcium carbonate at 800 degree for 2 hours in vacuum. The decomposition of nitrous oxide was carried out in a conventional flow reactor, and the surface sites and absorbed species were characterized by the Bier's analytical method. And the reactivity of the absorbed oxygen species was tested by use of temperature probe reaction with ethane. This figure shows the outlet partial pressure of nitrogen and oxygen during the process of nitrous oxide decomposition of calcium oxide. At the initial period of reaction, the outlet partial pressure of nitrogen is much larger than the partial pressure of oxygen expected from the stoichiometric material of this reaction. So this suggests that the absorbed oxygen species are formed of calcium oxide by the decomposition of nitrous oxide. This figure shows the temperature probe and desorption profile of an absorbed oxygen species formed of calcium oxide by the decomposition of nitrous oxide. As you see, there's a strong peak appears around 600 and 700 Kelvin, and this peak increases with the increase of the reaction time for the decomposition of nitrous oxide. For the catalyst exposed to the nitrous oxide for 60 minutes, this one, the amount of absorbed oxygen species reached about 4.0 micromole per square meter. This corresponds to 7% of the surface coverage. So that the trend amount of absorbed oxygen species from calcium oxide by the decomposition of nitrous oxide. In great contrast, these observations for the catalyst exposed to the molecular oxygen, no desorption occurred. This figure shows the temperature program decomposition profiles of calcium peroxide. We can get the strong peak at 670 Kelvin at the same temperature, almost same temperature where we observe the desorption of oxygen. This suggests that these absorbed oxygen species is in peroxide forms. This figure shows the FTI aspect of absorbed oxygen species form of calcium oxide by the decomposition of nitrous oxide. As you see this, we can get the peak at 880 wave number, and this peak increases with reaction time for the decomposition of nitrous oxide. And according to literature, this is ascribed to the peroxide species in sidon structure. Since argon ions, metal peroxide are hydrolyzed in an acidic solution to give the hydrogen peroxide, the samples having various amounts of adsorbed oxygen were getting to the sulfuric acid solution, and the formation of hydrogen peroxide was tested by use of titanium species of an indicator. This is the spectra of the solution. As you can see from this figure, the peaks, absorption peak appears around 0.7 nanometer, which is ascribed to the titanium fluoride species, so that the hydrogen peroxide will form by hydrolysis of adsorbed oxygen species from calcium oxide by the decomposition of nitrous oxide. From the intensity of this peak, we can determine the amount of hydrogen peroxide formed, and this amount is plotted against the amount of oxygen pre-adsorbed. As you see this from this figure, the amount of hydrogen peroxide is practically the same as that the amount of adsorbed oxygen pre-adsorbed. And so the adsorbed oxygen species are almost completely transformed to hydrogen peroxide through this process in acidic solution. On the basis of these results, we concluded that the peroxide species were formed by the decomposition of nitrous oxide on calcium oxide. On the basis of temperature flow absorption profiles, for samples having various amounts of adsorbed oxygen species, we can determine the rate of absorption at a given temperature and given amount of absorption, so that we can determine the activation energy of the absorption and the absorption of this is plot against this is plot of activation energy of the desorption of oxygen against the amount of adsorbed oxygen species. At the smaller amount of absorption, the activation energy was marked at around 44 or 45 kilocalories per mole. But with the increasing amount of absorption, the activation energy decreased rapidly, and staying at around 31 kilocalories per mole for a wide range of adsorbed amount. This suggests that the surface site for the peroxide species are non-homogeneous. For examination of the surface sites for the peroxide species, for the luminescence spectra were obtained for the samples having various amounts of adsorbed oxygen species. This is spectra. We can see a strong peak at 300 and 400 nanometer in excitation and emission spectra. This is ascribed to the surface sites with potential number 4. And this peak decreased with increasing amount of adsorbed oxygen. Since we didn't observe any peaks ascribed to the surface sites, we didn't observe any surface sites of the ascribed to the we didn't observe any peaks ascribed to the surface site in potential number 3. According to closure, the peaks spread to the surface sites with coordination number 5 is located below 220 nanometer in exciting spectra, so that we can see the energy that spread to these sites. This shows the intensity of the excitation peak at 298 nanometer, which I showed you, against the amount of the absorbed oxygen species. With the increased amount of the absorption, the intensity of the peak decreases rapidly, and that the amount of absorption of 0.15 micromolar per square meter, this corresponds to only 1% of the surface coverage. The intensity decreased decreased by 90%. This indicates that the peroxide species were located on the surface side with coordination number 4 at a smaller amount of absorption. However, since the amount of absorbed oxygen species was reached as much as 27% of the surface coverage, the rest of the oxygen species is probably located on the surface sites, abundantly present on the surface of calcium side. According to Stone and other authors, the 100 cases is preferentially exposed on the surface of calcium side. We concluded that the peroxide species were located on the surface side with coordination number 5 at the large amount of the oxygen species. This shows the outlet partial pressure of ethylene formed in the course of temperature program reaction runs with ethylene. As you see this in the absence of oxygen species, this 1A, the ethylene formed slowly but increased rapidly above 700 Kelvin. This is ascribed to the dehydrogenation of ethane, because we observed a plenty amount of hydrogen in the outflow. But in the presence of oxygen, we could see the two strong peak at around 600 and 700 Kelvin. At a small amount of absorption, the peak at 600 appears in preference to this peak, so that this is ascribed. This is probably ascribed to the surface sites with coordination number 4. But with the increasing amount of absorbed oxygen species, this peak grows faster than this one. So this will be ascribed to the surface sites with coordination number 5. Since we didn't observe any oxygen and hydrogen in the outflow, we concluded that the oxidative dehydrogenation of ethane occurred in this temperature range in the presence of oxygen. On the basis of the amount of oxygen consumed, and the amount of pre-absorbed oxygen species, we can determine the selectivity for the oxidative dehydrogenation ethane. This is a plot between the selectivity and the amount of absorbed oxygen species. At a small amount of absorption, selectivity approaches about 80%, but with increasing amount of absorption, absorbed oxygen species selectivity decreases rapidly. Hence, we concluded that the surface peroxide species bound to the surface sites with coordination number 4 are more active and selective than the peroxide species formed on the surface site with coordination number 5 for the oxidative dehydrogenation of ESN. In conclusion, we can say that a considerable amount of surface peroxide species were formed on calcium site by the decomposition of nitrous oxide. And secondly, surface peroxide species were preferentially held on the surface site with lower coordination numbers at small amounts of adsorption, while at large amounts of adsorption, surface peroxide species were held on surface sites with higher coordination numbers. And thirdly, surface peroxide species formed on sites with lower coordination numbers were more active and selective than the surface peroxide species formed on surface sites with higher coordination. Thank you for your attention.
Now, the presentation is open for the discussion. Do you have any questions or comments?
I'm very interested to study oxygen species. Usually, the nitric oxide constitutes giving the atomic oxygen species with 1 electron charge. You include the oxygen species in molecular form, in peroxide form. That means on the surface, the peroxide form and the atomic form will be equilibrated. Radically equilibrated between the atomic form and the molecular form. Is it true? And in this case, the second question is, recently people argued the mechanism of the surface for method of dental coupling. One model supported by Professor Lansford, who supported the oxygen minus would be a key species for the reaction. But for Professor Oscar, who proposed the oxygen 2 minus in peroxide is very important. If you believe the oxygen minus and oxygen 2 minus would be equivalent on surface, the two models will be equal. Will be identical.
I can hear.
The oxygen 1 oxygen and the oxygen will be the same species on the surface, I think. Just a short, I ask you a question. If the oxygen species with atomic form and molecular form will be the same on the surface, because the nitric oxide becomes giving atomic form directly.
Firstly, yes, I suppose so. By the decomposition of nitrous oxide, yes. You're asking the mechanism of the formation of peroxide species on the surface. Actually, yeah, your question.
Yeah. Okay. Nitric oxide composed with giving atomic form.
Yeah, right.
But you suggest you reflect the molecule for the oxide. So the question is, if the two species will expect equilibrium very rapidly on the surface.
Probably your question is related to the mechanism of reactions, the formation of peroxide species, I guess. To know the mechanism is very important for us and for elucidation of the formation of peroxide species as well. And since we didn't study the mechanism of the formation of the surface peroxide species, I can't give you the definite answers, but I think the O- species probably formed first. Well, that may be located on the surface side where vacant, the unsaturated surface sides first, and react with probably with the lattice oxygen to form the peroxide species. And peroxide. Then peroxide, this is the formation of peroxide species. And for the case, probably you are interested in the desorption of peroxide species. So I think the desorption of peroxide species is probably takes place recombination of two peroxide species, giving the molecular oxygen gas phase, and the other one is the O2- species in the lattice of the calcium side.
Thank you. I'm very interested in your talking. My question is you use infrared spectroscopy and use fluorescence spectroscopy and measure the oxygen species. My question is this, at the 880 weak number species and at the excitation fluorescence spectroscopy at the 298 nanometer. Is the same species or different species?
298.
Yeah, 298. That's it. It's same species.
No, well, the 290 nanometers,
Yes.
you are talking about, this has spread to the surface side with coordination number 4.
Yes.
But 80 wave numbers peak is the peroxide species vibration